Hi everyone, today we're going to introduce the Schrödinger equation. We will explain the meaning of wave functions, relate operators to measurable observations, and identify eigenvalues and eigenfunctions. Alright, let's get into it. The Schrödinger equation is one of the most important equations in all of quantum mechanics. It is a differential equation that when solved gives a complete description of how a quantum system evolves over time. The equation shown here is known as the time-dependent Schrödinger equation as it depends on both the coordinates and time. The first term is the Hamiltonian. The Hamiltonian describes the energy components of the system. The next term is the wave function. The wave function completely describes the quantum system. It appears on both the left and right side of the Schrödinger equation. Last is the time evolution of the system. If the system does not depend on time, then the Hamiltonian will be time independent. The right-hand portion of the equation then becomes a constant. This equation is known as the time-independent Schrödinger equation. It only depends on the coordinates and not time. We can then rewrite the equation. The wave function, being independent of time, represents standing waves, like the wave pattern made when plucking a guitar string. The constant on the right-hand side of the equation is the energy of the system. The time-independent Schrödinger equation is used to solve the energy of quantum systems. This is the version of the Schrödinger equation that we will use for the class. We will assume that our Hamiltonian, and hence our wave function, is independent of time. The Hamiltonian is an operator. That is, it operates on a function to modify that function. In the example shown here, the first derivative with respect to x is the operator. It is operating on e to the kx to give a new function, ke to the kx. In this particular case, the new function is the same as the old, multiplied by a constant. Operators in quantum mechanics represent observables. Every observable has a corresponding operator. The two most common that we will use are the position operator, which is simply the variable x, and the momentum operator, which involves taking the first derivative of the function. The observable that the Hamiltonian operator represents is the total energy of the system. The Hamiltonian is the sum of all the potential energy terms and kinetic energy terms in the system. For example, if a ball was rolling down the hill, the Hamiltonian would represent the kinetic energy of the ball as it moves down and the potential energy related to how much farther it has to go down the hill. In operator math, we can write the Hamiltonian as the sum of the kinetic energy operator T and the potential energy operator V. The kinetic energy is 1/2 the mass times velocity squared. We can write this in terms of momentum. Momentum squared divided by 2 times the mass. Since this is in terms of momentum, we can now use our quantum mechanical momentum operator. The potential energy term depends on the system that we want to study. The wave function fully describes the quantum system. Quantum mechanics is a probabilistic theory, and the square of the wave function represents the probability of finding the particle. In the following example, the most likely place to find the particle is in the middle, where the wave function is the highest. The wave function is responsible for both the particle-like and the wave-like nature of the universe. Wave functions have some restrictions that we must place on them. First, they must be single-valued over all space. That is, for every position, there can only be one value of the wave function. For a one-dimensional system, that means that there must be only one value at each point in x. Next, the wave function must be continuous over all space. The function cannot suddenly break or be disjointed. Finally, the wave function must be square integrable over all space. If you integrate the wave function over all space, the value must be a constant, not infinity. This is due to the probabilistic nature of quantum mechanics. If we look at the Hamiltonian operating on our wave function, we get our wave function back, multiplied by the energy of the system. This is called an eigenvalue equation. The wave function is an eigenfunction, and the energy is an eigenvalue. These types of equations are important in quantum mechanics, as the eigenvalue is the observable that is directly measured. For example, when you measure the energy of the system, the values that you obtain will be identical to the allowed values for energy.